Okay, started the streaming on the YouTube channel. Today we will discuss first example, an example of distributed parameters modeling. The model we are going to discuss today is a GIS model applied to a large river catchment with the scope of evaluating the loads of nutrients in terms of nitrogen and phosphorus. The catchment we are going to model is the Po River catchment. It is a very large river in Europe, one of the largest rivers in Europe. And the territory that is producing loads is very large and relevant from the socio-economic point of view. The basis of this distributed parameter model is a GIS application. GIS is Geographical Information Systems. Here I have listed a series of tools, software tools, ArcInfo, ArcView, GRASS, MapInfo, and so on. I stress my relevance on the GRASS, Geographical Resource Analysis and Support System, that is an open source, very complete GIS system. It is very interesting because being open source, it is a cheap software tool, while the software provided by Esri, like ArcInfo, ArcView, and so on, are quite costly, expensive. In this context, GIS systems are employed for building support systems for land management, or in general decision support systems for the management of territories. And in particular, the application we are going to look at today is geographic modeling, that in our language may be defined as distributed parameters modeling. Distributed means that the parameters depends on space and time. So different value of the parameters describe different places. The possibility of building this kind of models is linked to the availability of large quantity of data, in particular satellite imageries coming from remote sensing. So satellite imageries produce pictures or descriptions of large portion of territories. In particular, let's give a short review on GIS. GIS are used for describing a portion of land. The idea is that of combining different information layers, and the layers used depend, of course, on the purpose of the model. Some examples of geographic information system modeling are, for example, a model for finding the best location for a shop, or studies of social characteristics like crime, unemployment, or analysis of a factor of environmental damage, that is the topic that is of interest for environmental engineers. The idea is that of combining different data layers, for example, a picture of reality, maybe a digital elevation model, then information on streets, building, and customers, that are the layers that may be employed for building a DSS for finding the best location for a shop. A GIS system consists of hardware, computer and peripherals like plotters, software, ArcInfo, ArcView, MapInfo, GRASS, data, remote sensing data, for example, satellite imageries or pictures. Then you need staff, people that is trained for managing this large quantity of data. And then you need also some source of training for preparing the staff for managing these large quantities of data. It is important to develop careful analysis of methodology employed in order to interpret the results generated by GIS analysis. So GIS is a tool, quite complex, sophisticated tool that allows us to manage large quantities of information. The elements of these systems are coordinate systems, that is made up of scales, projections, datum. Coordinate system is a way of describing or identifying different portions of a territory. Then, on the basis of these coordinate systems, you shall collect data files, what are called shape files in the Esri systems, so ArcView, ArcInfo, and so on. Shape files are files made of three different types of objects. First one is points, second one is vectors, and the third one are maps. Excuse me. It is important to notice that while points and vectors are not dependent on the scales or on the resolution of your descriptions, because in point and vectors shape files, you have a list of objects that are identified, for example, in points by a triplet of coordinates, or in vectors by a starting point, a direction, and a length. On the contrary, maps or raster maps are dependent on the scales. Raster maps are subdivisions of territory in cells, so that you understand that the cell's subdivision is fixed. So, for example, you may describe a portion of land by employing 1,000 cells, or you may decuplicate the resolution and employ a raster map of 10,000 cells. So you understand that the dimension of a shapefile and the resolution as well depends on the quantity of information that you may include in the description of your portion of land. Once you have assembled your description into geometrical objects, points, vectors, and raster maps, to each of these objects in the shapefile, you may attribute data. Data figures in the form of attributes that are in general tables of values that characterize each of the objects in the shapefiles. So these are the basic information or very basic definition we employ or we need for building a GIS model. Now let's give a look to a specific model that is called monaries. It is the acronym for Modeling Nutrient Emissions into River Systems. Mces was developed in the late 90s by Horst Behrendt in Berlin, Germany, and it was built on as a support tool for a research project on water, on the quality of water, and it was developed by the Federal Agency for the Environment. Umweltbundesamt means environment. What are the characteristics of this model? It is a steady state model, so we are taking pictures at a certain moment in time. Means, for example, seasonal pictures or monthly pictures or yearly pictures. It is a distributed parameters model. The spatial scale is that of a hydrologic unit, what in this context may be called sub-basins. And in terms of length, we talk about dimension larger than 15 square kilometers. So you understand that this model has quite a rough, or if you want, low spatial scale. And concerning the temporal scale, again, we have quite a rough or low temporal scale, because typically, and in particular for the application we're going to look at today, we employ an annual or seasonal or pluriannual temporal scale. The idea of a model is about evaluating the emissions and the residual loads conveyed through different pathways, particular groundwater, surface runoff, and so on, and fraction due to different sources, that may be agricultural, civil, urban spread, and so on. So the idea of a model is that to provide an estimation of nutrient loads, in this case, in particular nitrogen and phosphorus, on a large river basin, and also to establish which are the most significant sources of these nutrient loads, in terms of identifying if resources are agricultural or civil or urban runoff and so on, and also that of identifying which are the most relevant pathways through which these nutrient loads are conveyed toward the basin closure. This table, it is a list of the input data employed by the model. Please keep in mind that we are thinking to a specific application of a model, that is the Po catchment river. So the input data concern general information, for example, areas of the sub-basins in square kilometers, flows and loads, so annual average loads, annual average discharge, or annual average loads of dissolved inorganic nitrogen, annual average loads of total phosphorus, annual average loads of suspended solids. These are all data that you need as input data to build up and to calibrate at least the water discharge part of the model. Then we need statistics on municipalities, in particular number of inhabitants per sub-basin. I recall you that the unit here is the hydrologic unit, so a sub-basin. A sub-basin is a portion of land for which you may identify a single closure or a single point of outflow from that portion of land. So for each one of the sub-basin, you shall indicate we need the number of inhabitants and the surface of arable land in square kilometers. Then, for each subbasin, we shall include a large set of information. For example, the surface of urban areas in square kilometers, industrial areas, or vegetated or arable lands in square kilometers, or pasture lands, or forests, or meadows, or wetlands, and so on. So we distinguish the land use in terms of how much square kilometers of different land use are present in each one of the hydrological unit, or in each one of the subunits, but in this context we will call subbasins. In particular, for each of these subbasins, we shall also include information concerning the pedology, so annual mean erosion, type of surface terrain, is sand or clay, or for example, wetlands, water, seawater bodies, and so on. We have to include also information concerning the geology. In particular, we have only 3 classes: the area that are made up of terrain non-consolidated, in which the aquifer are deep, so there is not shallow aquifers, so there is a strong interaction between the surface and the groundwater system. Areas that are built up from terrains that are non-consolidated, in which the groundwater or the aquifers are deep, so there is not much interaction between surface and groundwater, or areas that are built or that are constituted by consolidated terrains. Of course, these differentiations in the geology are needed in order to qualify the flows that link surface activities on the land and the effect on the groundwater. Then other important information are the slopes. So for each subbasin, we indicate percent of average, median, or average slope in the subbasins, percentages. We have to include some meteorological data, like precipitation and atmospheric deposition. We have data concerning annual averages, or summer or winter averages, in order to distinguish for processes that are more relevant in the summer or in winter. Then we have to include information concerning the agricultural activities, and this is the agricultural surplus. So for each subbasin, we have numbers describing the kilogram per hectares per years of nitrogen, and the kilogram per hectares on the long time for phosphorus. Why on the long time? Because phosphorus has a much longer times for propagation. So while for nitrogen we employ yearly numbers, for phosphorus we employ decadal numbers, so phosphorus surplus on 10 years, for example. And then we have to include several information concerning the urban systems. Number of inhabitants for each subbasins, number of inhabitants that are connected to a wastewater network, number of inhabitants connected to a sewage, number of inhabitants connected to a sewage and treated through wastewater treatment plants, the average length of the sewage system, sewage network, the average length of the mixed sewage network. So these are gray and black waters. And then phosphorus and nitrogen loads discharged by the wastewater treatment plants present on the territory. So you see here and here you need a very large amount of data for each subbasins in order to describe your territory. Once you have collected all this data, you assemble this data into a series of spreadsheet files. In particular, Mces is based on Excel. Each spreadsheet file refers to a specific pathway. In pathways, in particular, we have eight pathways: atmospheric deposition, surplus, erosion, groundwater flows, overland flow, point sources. Point sources is wastewater treatment plant. Urban systems is urban runoff, and the background. All these pathways convey the calculator of estimating nutrient surplus in the topsoil through different processes. Here you have erosion processes, surface runoff. These are nutrient leaching from the root zone, so these are interaction to the groundwater systems. When here you have atmospheric deposition, here you have urban runoff, and here you have point sources, wastewater treatment plants. All the nutrients conveyed by these different pathways are combined into an estimation of the total nutrient emitted into river systems. When the model itself includes a nutrient retention model that tries to estimate the self-purification capacity of surface water bodies. But you know that self-purification is a characteristic of surface water bodies. For example, you know that in surface water bodies, you may have denitrifications that takes away nitrogen from dissolved quota in water and transfer it to the atmosphere. Or you may have filtering effect of the soils that may trap, for example, phosphorus into solids. So after the estimation of emissions, you have an estimation of nutrient retentions. Then you have an estimation of nutrient load into the rivers. And as the final output of the model, you have nutrient inputs into the seas. So the nutrient loads that are vehiculated from the river system toward the coastal areas. This model was developed in the context of the EuroCat project, what was an FP5 research project, European research project, that involved several large river catchments in Europe, trying to estimate what was the effect of anthropic activities on the water quality of the coastal areas. So the first problem was that of estimating the effect of human activities on the territory, in terms of production of nutrient loads. Let's give a look more in detail to the pathways. The atmospheric deposition pathway considers the emissions due to direct atmospheric deposition on water surfaces. Atmospheric deposition is used also in the pathways erosion, urban systems, groundwater, and tile drainage. So this is why we need meteorological data. The surplus pathway calculates the concentration of nitrogen and phosphorus in the soil as a function of the clay content and amount of fertilizer manure used in the agricultural soil. So in this pathway, we estimate the difference between the quantity of nutrients that are applied to a soil per unit surface per unit time, and the quantity of nutrients that are brought away by yield. So this surplus calculates as a difference between the manure fertilizer employed for agricultural activity and the nitrogen and phosphorus taken away by agricultural yields. Of course, in this case, in the surplus pathway, it is not calculating a value of emissions, but the results of this pathway are used in the pathway erosions, groundwater, and tile drainage. Erosions describes the erosion from agricultural land, but takes into account for a significant release of suspended solids and nutrients. In particular, you may recall that phosphorus goes with the suspended solids. Then the groundwater pathways describes the effect of precipitation that infiltrates and is loaded of nutrients from the soils. Before arriving to the closure, several processes can take place, such as denitrification, phosphorus release under anaerobic condition, which depends on soil characteristics and so on. In particular, characteristics of the soil linked to the pH and clay content. Of course, groundwater, as we will see, is one of the most important emissions pathways. The overland flow pathway describes surface runoff in areas that are not paved, so not urban areas. Here, the nutrient concentration are determined by the soil type. So we tries to take into account the effect of filtering due to soil. The point source pathway describes the effect of discharges due to sewage and treatment plants and industries. The urban system pathway describes during the events of rain, but the effect that most of the water collected from drains is bothered in the receptor water body quite quickly. The tile drainage is related to emissions from agricultural land drainage systems and considers calculated surplus concentration and denitrification, while the last pathway, that is background, calculates the total emission without the anthropogenic contribution. So the natural systems emission due to the soil coverage, land cover, soil type, and atmospheric effect, without the effect due to urban systems in terms of agricultural activities or in terms of wastewater treatment or sewage systems. So we collect all this large amount of input data that we may describe this as the catchment description. And these are collected into the first input spreadsheet that is called basic info. And then from this spreadsheet, the nutrient loads calculated are veiculated through different spreadsheets: atmospheric deposition, erosion, overland flow, tile drainage, groundwater, urban areas, and point sources. And the results or the output data are produced into a further spreadsheet file that is called moneries, in which you have figures on nutrient emissions, different pathways, different sources. So a kind of model report. So you see, this is a quite sophisticated model that describes a large environmental system, a river system, a river catchment system, and through the estimation of the different processes that are included into these spreadsheets, the model produces an estimation of nutrient emissions. These are description, for example, of the pathways included to the model in the description of urban areas. This is just a picture to show you how sophisticated or complex is the model. For example, you have effects due to household or industrial indirect discharges. You have emission due to traffic. You have emission due to litter fall or to atmospheric deposition. All these combine to produce a load to paved areas and unpaved areas. And these different contributions are then separated into groundwater, separate sewer system, combined sewer system, sewers without wastewater treatment plants. So this is sewage water that are directly discharged on land, separate sewer system, and nutrient loads that are directly conveyed to the groundwater. Of course, information concerning wastewater treatment plants and information concerning overflows due to strong rainy events contributes onto the estimation of nutrient load generation by wastewater treatment plants on surface water. These are brought from wastewater treatment plants and from overland overflows in wastewater treatment plants and through combined sewer overflows. All these nutrient loads are conveyed to surface water recipients. Finally, we employ a very simplified retention model that is based on several data, empirical data, in which we have we study the ratio between load and emissions. So emission is what it is generated on a particular subbasin, and the load is what of this generated is transferred to the surface water system. And of course, this ratio load over emission depends on discharge, Q, and over two parameters, small a and small b. And we have, for example, more than 50 points, data points, all over Europe that were employed to calibrate this retention model in terms of finding good values of a parameter A and B all over Europe in terms of total phosphorus transport over total phosphorus emitted. So we have how much the ratio between what it is produced and what it is transported toward water receiving water body as a function of a specific runoff. We have this for total phosphorus, and we have also this for dissolved inorganic nitrogen. So you see that the retention model, it is an empirical model based on a large quantity of empirical data or observational data that comes from all over Europe. So come from several river basins all over Europe. How did we make the application onto a PO catchment? This is a digital elevation model of the PO catchment. You see, we may identify some areas: the Alpine area, the Alps, mountains; the Apennines area, again, mountains. Then the Po Valley or the Po Plain, which is a flat land that receives all the water coming from the Alps and from the Apennines. Then from this network of surface water bodies, the water is conveyed through the main river pathway. These are the sources of the Po River, and these are the main river pathways through the cities of Turin, and then coming out and receiving water coming from the area of Milan and bringing it through the main river pathway down to this point, that is the closure of the basins in Ponte Lago Scuro Ferrara, that is the place at which we collect nutrient loads data that are useful in order to calibrate the model. So we are estimating by this model what are the effects of the anthropic activity in a very large river catchment in terms of producing nutrient loads that reaches the Northern Adriatic Sea. Please note that the area on which we are applying this model is very large, more than 73,000 square kilometers. And please note that the population resident or living in this area is also a very large quantity, very large number, 17 millions of inhabitants. So 17 millions, if you consider that Italy is around 60 millions, 70 millions is something less than 1/3 of all the Italian population is living in this area. So you may understand that this area has a very relevant national economic importance. In terms of GDP, where 40% of the GDP is produced in this area, 46% of employment for Italy comes from this area. We have 37% of industrial production, but we have also a very significant agricultural activity, 35%, and also zootechnical or cattle raising activity up to 55%. In this area, 45% or 3.4 million hectares are agricultural arable land. So the importance of agricultural activity in this area is really great, big, large. We have more than 1 million hectares that are permanent meadows and pasture lands, on which we grow 4 million cattle and 5 million pigs. So you see the numbers of animals is comparable with the numbers of humans living on the area. So we have around 10, more than 10 millions, around 10 million animals that are grown in this area. The Po River, hydraulically speaking, is really a monster. It is one of the 6 largest rivers in Europe. And when I mean large, when I say large, I mean that the discharge in Ponte Lago Scuro is more than 1,500 cubic meters per second of water that transits at the basin closures in Ponte Lago Scuro. Nutrient loads, as estimated by the Po River management authorities in the past years, and we are talking about late 80s and 90s of the last centuries, are around 100,000 tons per year of nitrogen and 9,000 tons per year of phosphorus. Please keep in mind these figures, because these figures are useful to compare the results of the model application. So, as a rule of thumb, we may say that 100,000 tons of nitrogen is produced and 9,000 tons of phosphorus is produced in this area, and it is discharged on the Northern Adriatic. Of these loads, 63% for nitrogen comes from diffuse sources, while 42% for phosphorus comes from diffuse sources. And the others comes from point sources. So you see also that the importance of diffuse contributions is high in this area. Why are we interested in evaluating nutrient and phosphorus loads in Northern Adriatic? Because as you may imagine, and as it will be clear next week when we will discuss nutrient limitation, nitrogen and phosphorus are the limiting nutrients for primary production in water ecosystems, and in particular in coastal zones, in coastal areas. These nutrient loads may be a source of concerns due to the production or due to the appearance of the phenomenon of eutrophication, so dystrophic algal blooms that may have a significant effect on the water quality in the coastal areas. In order to build up the application of monorays, we subdivide the Po catchment into 33 subbasins. This is the subdivisions. For each subbasin, we shall identify a basin closure. So, for example, the Wool Po River basin closure is here in Ponte Lago Scuro, while, for example, if we consider the subbasin related to Milan, this is the large city of Milan, violet urban area. For the city of Milan, the basin closure is in this point, so it is the Lambro River that discharges into the main Po River flow. This indicates the main Po River flow, so flowing from Torino down to the area of Milano, Cremona, Mantova, down to Ponte Lago Scuro, Ferrara. So this is the main Po River flow. For example, of each one of these subbasins, we shall identify a basin closure. For example, for this subbasin 11, the basin closure is identified here. In Pavia, this red gauge station, so we have to identify different discharge gauge stations in which we have figures concerning the water discharge, so water quantity flowing in the subbasin closure, and quality gauging stations, so stations in which you have information concerning water qualities. Triangles are quality gauging stations, and squares, gray squares, refers to discharge gauging stations. For example, let us focus on the subbasin 11. We said that the gauging station for subbasin 11 is here near Pavia, but we shall identify immediately a difference between the net and the gross of the total surface, the total discharge area. For example, for the subbasin 11, the net discharge area or the net surface contributing to the gauging station here in Pavia is related to the total area of the subbasin 11, while the total surface contributing to what is passing in this gauging station in Pavia is made not only by the surface in these subbasins, but also from the surface of all the other subbasins that are contributing through different pathways to what passes in Pavia. For example, in this case, in the case of subbasin 11, the net surface area is this one, represented by the area of this subbasin, while the total contributing area is not only this one, but is this one plus the subbasin area 6, plus the subbasin 9, plus the subbasin 10, plus the subbasin 8, and so on. So all these subbasins are contributing to what is passing into Pavia gauging station. Is it clear? Of course, we may focus only on what is passing, what is happening on the basin 11, but the water that is arriving in Pavia is also bringing the effects of loads generated in other basins. So the total area contributing to the loads in Pavia are not only the area of subbasin 11, but also the area of all the other subbasins contributing to the water that is passing to the Pavia gauging station. So we have to identify 33 subbasins. For each subbasin, a gauge station or gauging stations in terms of discharge and water quality. For each one of these subbasins, we have to identify catchment IDs, the net catchment area, the total catchment area, and the equation that converts from the total to the net catchment area. Is it clear? Net catchment area, only the area of the subbasin. Total catchment area is the area of the subbasin plus the area of all the other subbasins that contributes to the water flowing to the closer gauging station of basins 11 due to the fact that the other subbasins are contributing to our we say upstream. We may say upstream subbasins. Okay. Let's give a look how we collect information. In particular, now let's look to runoff and river load. We collect information in the period 1990-1995. The total catchment runoff area. The source is the drainage authority of the Po river basins. We have average measures 1995. Nutrient loads, again, the source is the drainage authority of the Po river basin that provided us with information of dissolved inorganic nitrogen, total phosphorus. Now you should notice that we made a very large, strong approximation by simply calculating the loads as the product of discharge times the concentration. So total nitrogen loads, for example, at each gauging station or closure point of the basins are calculated by multiplying the discharge provided or the total catchment runoff provided by the ADBP multiplied by the concentration, total concentration of nitrogen provided. You know, you understand that, of course, this is already a large approximation because there are correlations between concentration and discharge. This would be true if the relationship between discharge and concentration were not correlated, but in reality we know that while the discharge is growing, the concentration grows as well, and in particular, let me see if I can make some annotation. If this is time, and if this is discharge, this relationship could be true if the relationship between time and discharge is linear. In reality, we know that the relationship between time and discharge has more a saturation behavior, because of course, you know that while the discharge grows, you have a first effect of washout, and when the discharge increases further, the concentration stops increasing. So the first strong approximation is that of employing a linear relationship between load and discharge by multiplying discharge times concentrations. Then we have to include for all the 33 subbasins all the information concerning the activity of humans. How do we did that? We employed the ISTAT subunits in Italy. The ISTAT subunits are the subunits that are ISTAT is the Italian statistical agency. So are the units employed by the National Statistical Agency for making statistics on the territory. So what we have is that for each of these subunits, and we have a totality of more than 6,000 ISTAT subunits, we have a lot of data concerning, for example, population densities, arable lands, and things like that. The problem is that, of course, the boundaries of the ISTAT subunits do not always coincide with the boundary of a subbasin or hydrological subunit. So this means that on the boundaries, we had to subdivide those ISTAT subunits that pertain to different hydrological subunits, so that as a linear proportion of the surface included in the different hydrological subunits, we attributed a proportion of the figures pertaining to each ISTAT subunits onto the different hydrological subunits. This is a matter of GIS calculations. So we had several layers concerning, for example, the ISTAT subunits, and several layers concerning, for example, the agricultural subunit. And then we had to make some kind of GIS calculation in order to decide which portion of the figures contained in the 6,000, more than 6,000 ISTAT subunits pertained to the different hydrological subunits or catchments, subcatchments. In particular, the ISTAT subunits, the information coming from the ISTAT subunits concern inhabitants and the total area coming from statistical reports and the total arable land. The sources for this data were ISTAT, so National Institutes for Statistics, and the Drainage Authority of the Poor River Basins. Then we had to include a set of information describing the geographical situation. In particular, we employed the CORIN 2 land use. This was provided by the European Environmental Agency, EEA. These are satellite imageries describing different land use. In particular, red are urban areas, blue, of course, are water bodies, and greens with different colors, greens and brownish, refers to different land use, going from forest, through meadows, pasture lands, wetlands, arable land, and agricultural land, and so on. So the land use information comes from satellite imageries produced by the CORIN 2 project. Again, for the geology, we had a very rough description of geology. In particular, we have a simple classification in 4 classes: consolidated high porosity, consolidated impermeable, unconsolidated deep groundwater, and consolidated shallow groundwater. So these classes try to describe the strengths of interaction between what happens on the surface of the basins and what happened in the groundwater. So again, with a set of GIS calculations, we calculated how much in terms of surfaces of the different classes fall into the different 33 hydrological subunits. Of a digital elevation model, again, these are provided by the USGS data. Again, we have to calculate the slope, in particular, because the slope is a relevant information concerning what enters into estimation due to runoff, surface runoff. So we calculate the slope, and as you can see, the slope here is 0 because we are in a flatten, while the slope here is quite elevated due to the fact that we are in mountainous areas. Again, we had to include precipitation, so atmospheric meteorological information. This is the source is the panel for climate change, global panel for climate change, in which we have information on precipitation, average precipitation, cumulative for the year 1995. These are for summer 1995, winter 1995, and then we have the long-term average in the period 60s to 90s. You see that the resolution is very low. So we have kind of boxes of 100 kilometer size. So the precipitations resolution layers are very low. But what we have calculated here is the quantity of surfaces pertaining to each hydrological subunit that was characterized by this value of precipitation. For the evapotranspiration, we have the same, for the evapotranspiration, we employed the United Nations Environmental Program, where even lower resolutions. Evapotranspiration is linked to the land cover, essentially, and it is obtained by classical model what was provided by FAO, that is a UN agency for FAO, it is the Food and Agricultural Organization, that provides a very standard model for the estimation of evapotranspiration in terms of agricultural crops, so the potential of evapotranspiration for different agricultural crops. And then we have even lower resolution in terms of atmospheric deposition. We employed the values, the figure provided by IDB, that is the University Institution for the study of geographical study, the institution to which Horst Behrendt belonged, but has developed the model. So in particular, we employed averages of means for the 85 or 96 of grams of nitrogen and grams of nitrogen per square meters in the average in these years, but these figures were provided by Horst Behrendt personal communications. Then we had to estimate the effects of agricultural activities. This is very complicated because you have to have information concerning the employment, the use of manure and fertilizers in different areas. So you have to discuss with farmers and ask them how much manure are you spreading on your field, how much fertilizer are you employing, and then what are you growing in this area, and then you have to employ estimation of a nutrient in terms of nitrogen and phosphorus that are transferred to the crops. And then we employed a very rough formulations for estimating agricultural surplus in terms of nitrogen and phosphorus surplus by saying that the fertilizer plus manure in terms of nitrogen and phosphorus, kilograms per hectare per year of nitrogen, or kilogram per hectares in the long terms for phosphorus, long terms meaning 50 years. So we apply fertilizer plus manure minus what is taken away by yield. So you understand that, but also this, the collection of this data was quite complex because we had to have information concerning the employment of fertilizer and manure and information concerning the crops that are grown in a particular territory. These information are not always available, especially because farmers do not like to distribute to this information because they, you know, in Europe we have the so-called CAP, Common Agricultural Practice, that is a set of laws that forces farmers to limit the use of fertilizer and manure on the agricultural land. So from one side, you not always have reliable information on this. And the second aspect concerning yield is, of course, that farmers do not like very much to let the institution knows how much production they are having on their fields. This is, of course, because production is linked to taxations, and in particular in Italy, we have very large difficulties in finding these figures. But we refer to agricultural consortia. Agricultural consortia are consortia association of farmers. So agricultural consortium can provide us with quite reliable average information concerning these figures. So we calculated the agricultural surplus by simply making a difference between what it is put or provided into a portion of territory in terms of fertilizer and manure, nitrogen and phosphorus content of fertilizer and manure, minus what it was taken away by crops, nitrogen and phosphorus. You understand that we made a very large approximations in doing this kind of calculations, of course. But as we will see, nevertheless, the model is working quite well. So this is the figures, layers concerning nitrogen surplus in terms of kilograms of nitrogen per year per hectare. So you see that we have a most strongly agricultural areas that are the dark reddish brownish ones, and the less strong agricultural areas that are pinkish areas. This is for nitrogen surplus. We have a similar picture for phosphorus surplus as well. Okay, then we turn to urban systems. Here again, we have a lot of information, but is very approximate. We have to calculate the total inhabitants that are connected to sewage systems, the total inhabitants that are treated, and the total phosphorus and nitrogen loads discharged by wastewater treatment plants, and the length of combined and separated sewers. So for each sub-basis, we gathered all these informations, and we sum and we obtain a figure for each sub-basins, and these figures goes into the input information, urban systems. Let's go back now to the basic info, general information. These are the 33 subbasins. This is the high Po river system going down to the Delta Po. Delta Po is the output near Ponte Lago Scuro. Here, for each one of these subbasins, we have an ID. We have a gauge station ID. So for each one of these subbasins, we identify measuring or gauging station for discharge and for water qualities. Then we have a calculation concerning the catchment area and the net catchment area. Catchment area was calculated by GIS analysis, while the net catchment area is calculated again by GIS analysis. Of course, for each catchment, you see that the catchment area is larger than the net catchment area. This means that in some cases they are equal, meaning that there are not contributors. But in general, we may say that, for example, this is the case of the Ticino, in which the catchment area is larger than the net catchment area. These are square kilometers. If we go by including net catchment to catchment areas, of course, when we arrive to the delta or the discharge Ponte Lago Scuro, the closure of the whole Po catchment, we obtain the figure 73,000, more than 73,000 square kilometers, because in Ponte Lago Scuro, all the water that has been passing through the different hydrological subunits arrives in the output of the rivers. By doing this subdivision, then we start with the first calibration, and the first step in calibration procedure is that of calibrating discharge. You may look, these are one-to-one pictures. So this is the discharge measured and discharge calculated by the model. And again, this is discharge measured, the blue line, and discharge calculated by the model, the pink line, along the main Po river flow. So this is the distance from the source. It goes from zero. This is the distance from the spring. So we go from 0 up to 600 kilometers. That is the total river length, or river length. And this is the discharge calculated, compared over all the 33 subbasins. So here we have 33 points. And again, here we have 33 dots. You may observe the discharge calibration, and you may say, oh gosh, what a good model, you have calibrated perfectly the model. In reality, it is important to notice that we have somehow altered the behavior of the discharge calibration of a model in order to make it the most adherent to a real situation. So in particular, what we are doing here, we have changed the parameters describing nutrient flows, water flows in gauging stations, so that the nutrient flows in gauging stations are perfectly consistent with the nutrient flows measured. The nutrient flows calculated in the gauging station are perfectly consistent with nutrient flows, the discharge flows calculated, measured, along into the closed basin. In other terms, what we are doing here is what we are including our knowledge concerning the flow of water, so that we are forcing the model to reproduce almost perfectly water flows along the 33 subbasin. Why this? Because we are interested in dissolved inorganic nitrogen and total phosphorus flows. So what happens is that we calibrated the discharge perfectly, so that we changed the parameters of the model so that measured and observed, calculated and observed values of discharge coincide perfectly, and then we are concentrating what happens to nutrient loads. So what, do not look at suspended solids because it is problematic, but let us look what's happening in dissolved inorganic nitrogen and total phosphorus. These are the confrontation between measured values and calculated values. So on the vertical axis, we have calculated values by the model, and the horizontal, we have measured values in the gauging stations. What it is happening? It is happening that for the smaller hydrological units, we have a large error. So you know that you see that the points are very far away from the one-to-one line. While as we go on along the main Po river flow, the error becomes less and less relevant. So you see that for the larger basins, that of course corresponded to those basins that produce larger loads in terms of total phosphorus and dissolved inorganic loads, for the larger basins, the errors are minors. What does this mean? This means that the errors are compensating, the errors in one direction are compensating with errors in the other direction as we go along the main Po river flow. This is an evaluation of the errors. Again, we see that for the 33 subbasins, the violet bars refers to bigger errors, while the model is working well if the violet areas, the violet bars are smaller than the gray bar. So 29 and 33 subbasins, or the 32 subbasins, but is the closed basin, low Tanaro, we have a very small error in terms of the dissolved inorganic nitrogen, but also in terms of total phosphorus. And these are the reports produced by the models in the model's spreadsheet. Again, this is nitrogen, the comparison between dissolved inorganic nitrogen measured and calculated, the comparison between total phosphorus measured and calculated. And you see that going along the main Po river flow, so coming from the spring zero to the outlet Ponte Lago Scuro around 600 kilometers, we have quite a consistent behavior of a model. This is the violet. But more interestingly, if we look at this table provides the figures. This table tells us that the total emissions of nitrogen in tons per year from the total summation of the various pathways is 164,000 tons per year, while for phosphorus we are around 32,000 tons per year. Sorry, 7,000 tons per year. For nitrogen, 164,000, and for the phosphorus, 7,000. Now I ask you to recall the figure that we had provided in the beginning of the presentation, which we said that by different means, the drainage authority, management authority of River Po estimated 100,000 tons per year phosphorus, and 9,000 tons per year. So 100,000 tons per year nitrogen and 9,000 tons per year phosphorus. So you see that roughly this quantity is consistent with the other estimations. The other important information that you may gather from the report is the subdivision along with different pathways. For example, you immediately notice that for nitrogen loads, the groundwater pathway contribution is the largest one. And for example, for the phosphorus, the wastewater treatment plant of the urban systems, of the tile drainage, of the overland flows are the most significant contributing pathways. That is obvious because these pathways are those that are more impacted by solid transport, and you know that phosphorus goes with solid transport. So we have some indication here from this kind of analysis, which are the actions or the management actions that should be implemented in order to reduce nutrient loads from such kind of a large river basin. I recall you, this is a very large river catchment, more than 70,000 square kilometers, and we have built a very complex model in which we use a huge amount of information that was not of very low quality, but nevertheless, we obtain some indication concerning what's happening in the basins and concerning which are the sources on which you may act in order to reduce the effect of total nutrient loads. In particular, we may subdivide by subcatchments the contributions to the total nutrient loads generation by this basin. And we see that, for example, the Milano Pavia Piacenza catchment, subcatchment, is one of the most significant both for phosphorus and both for nitrogen. You may make the same analysis along the Po River in terms of changing with different colors the quality of the river, of the water flowing along the main Po River course, and in particular, as it is expected, of course, you may see that going toward the end part of the basin, we have the most significant concentration in terms of milligram per liter of total nitrogen. But you have also some small indication concerning, for example, this reddish area tells us that the area of Milan is contributing significantly to total quantity of nutrient concentration, total phosphorus, total nitrogen concentration into a river. Finally, by this kind of modeling effort, we have been able to evaluate future scenarios for the management of Po River catchment. We identified 6 scenarios, 2 business as usual scenarios, business as usual basic, business as usual high, or policy target at 3 levels, meaning implementation of policy for natural protection, 3 levels of policy implementation, and a deep green scenario. So we are deep green scenarios, we are very, very good. We implemented these scenarios by changing the basic info spreadsheet and evaluating the different nitrogen loads and phosphorus loads at the basin closures in Ponte Lago Scuro. In particular, we estimated percentage in terms of variation from the actual condition 2001 and the implementation of different scenarios 2008 and 2016 in different conditions. So we see that the business as usual pink and business as usual base scenarios are the scenarios that brought to an increment of 5% in nitrogen loads by 2016. And we had the same estimation for phosphorus, and in particular, we see that in the case of a very deep green scenarios, we may have a reduction up to 35% phosphorus loads onto the coastal area. Okay, by now we stop. If you have any question, I'm here. Next week we shall start discussing about the application, your application in work groups of the models. Okay, do you have any questions? Next week, we will start introducing MATLABs. Okay, I remain here 5 minutes more, then I close the classroom, and we will see next week with MATLAB.